Hello, and welcome to College Algebra, where we are talking about one-to-one functions and inverse functions today. So in your note packets, if you could just get that up and ready to go, we're going to try to do both parts of 6.2 today. Alrighty, and so now, with that being said, if we run out of time, then we'll probably finish it the next day, tomorrow. Okay, so here we go. First, we're going to talk about one-to-one functions. Okay, so one-to-one functions, first of all, have to be functions, which means that for every for every x, there's exactly one y value. Okay, so that's something that we've already talked about in this course. And now, in addition to that, for it to be one-to-one, not only does every x have to have one y value, but each y value needs to be unique or different. Okay? So what that means is that you're never going to have any repeated y values, and you're never going to have any repeated x values. Okay? So just looking here, for instance, we'll talk about this horizontal line test in a second. If this is my set of x values and this is my set of y values, this is what we call a map. Okay? Every x has one y value, right? Every x goes to one y value. So this is a function. However, it is not one-to-one because we're seeing a repetition right here where we have 8 going to -1 and 10 also going to -1. Okay, so this is a function, but it's not one-to-one. Okay? Now, a graph is very easy to determine if it's one-to-one or not. Okay? In order for it to be a function, remember the functions, I'll write this in here, functions pass the vertical line test. That we already know. And those functions that pass the vertical line test are going to be one-to-one if it passes the horizontal line test. Okay, so let's jump down to problem D. Okay, here we have a parabola, y equals x squared. You can see that it passes the vertical line test. So this is a function. However, if we take horizontal lines, okay, we are intersecting or hitting the parabola more than one time, so we are failing the horizontal line test. So this is another example of, yes, this is a function, but it is not one-to-one. Okay, so now let's quickly go through the rest on this page. Here we have all different x values and all different y values. So every x goes to one y, and every single y is different. So this is a function, and it is one-to-one. Okay, if you're not good at looking at it in this format, you could always go back to this. Put all your x's in one map, or one side of the map, and now put your y's in another one. 2 goes to -3, 1 goes to -4, 0 goes to -5. Here you can visually see it's one-to-one because every x goes to one spot and there's no repeated spots that they go to. Everything's different over here. Okay. This example here, right off the bat, we see that it's not going to be one-to-one because the y values are repeated. But this is a function because every x goes to one spot, goes to one y. So again, sometimes it helps if you draw the map. If you have -2, 1, and 0, then you got 4 and -4. -2 goes to 4, 1 also goes to 4, and 0 goes to -4. So every x has exactly one output or one y value. But right here, this y value was determined by two different x values. We can't have that. Okay, so we can't repeat and go to the same y value twice, kind of like what we did up here with this -1. Okay, so that's why this is not 1 to 1. I guess I don't need to write not, I'll just write no. All right, last problem on this page, another graph. Vertical line test. Looks good. Hits the graph one time every time I draw a vertical line. So this is a function. Horizontal line test. Looks like every horizontal line will hit the graph one time. So this is a function, and it is 1 to 1. Okay? So that's kind of how to determine if we have 1 to 1 functions, and that's going to be huge as far as finding inverses, which we'll talk about next. Okay, before we find inverses, we're going to talk about the definitions for inverses. Okay, so this is kind of a fancy definition up here. Here's what you need to know. Okay, basically, right here, we practiced this in the previous section, except we had like F and G, and then G and then F. So we had the composition. If you plug G into F, and you plug F into G, and both times you get X, okay, then F and G are inverses of each other, okay? And we use this notation here. We use F, and it looks like a -1 exponent. It's not an exponent. It means inverse, okay? But you would write it like if it were, okay? And essentially what inverses do are just reverse what the original function is doing. So if x is going to y, y will now go to x, okay? So that means that all the x's and y's will flip-flop, which then by default means that the domain becomes the range, and the range becomes the domain. Okay, this will make more sense as we do examples, but let's just kind of work through with several different forms, a table, an actual equation, and we'll go from there. Okay, so here we have, it looks like a map or a table. You can see it's 1 to 1, which is a requirement. Okay, in order for a function to have an inverse, it must be 1 to 1. Okay, that's huge. Okay, so a lot of times you'll see restrictions when you're doing these problems that kind of chop up the domain so that it is 1 to 1, and now you can find an inverse for it. Okay, but so in order for there to be an inverse function, the function that we start with has to be 1 to 1. Okay, and this one is. And now if we're just finding the inverse, everything flips. Okay, so instead of minutes of phone call being your input, now the cost is going to be your input, and the minutes will be your output. Okay, so now we have $1, $1.50, and $1.75. Okay, and then that matches up with 10 minutes of a phone call, 20 minutes, and then 30 minutes. Okay, so this is what our inverse function looks like. Our cost and minutes just reverse. Okay, now the domain of the inverse function, we can get this two ways. If we know the inverse, our domain is going to be the x values, the cost. So that'll be 1, 1.5, and 1.75. If we don't have that, and let's say a problem's asking us to find the domain of the inverse, well, another option I have is I know that everything reverses. So the range, which are the y values of the function, become the domain. Okay, so that's another way to think about it. Okay, and you can flip-flop that when we're finding the range. If we're finding the range of the inverse function, you can just look at the y values of the inverse rule or function. Or if you know that things are going to reverse, look for the domain of the original function, because that's going to be your range of the inverse. Okay? So that's kind of with tables how that works. As far as verifying inverse functions, the key is going to be right here. And we practiced this already in previous sections. We just didn't call this verifying that functions were inverses or not. But essentially you plug one function into the other one, make sure you get x, and then you flip-flop it and make sure that if you plug the other one into the g, for instance, that you also get x there. Okay? So here we have two potential functions that are inverses. We need to make sure that they are by doing the compositions and making sure we get x. Okay? So for part A, we do have to talk about the domain because there are restrictions. Okay, so if we look at f, you guys know that when we have fractions, we're never allowed to have 0 in the denominator. So here, we say that x cannot be 1. Okay, so we can't do this if x is 1. So we're working with the assumption that it's not. Similarly here with g, we can't divide by 0 here. So x could not be 0 there either. Okay, so working with these assumptions, now we're going to go ahead and do the compositions. Okay, so if I do f of g of x, that's going to be f of, plug in 1 over x plus 1 into g, into the g of x. And now this whole g of x function is going to get plugged into the x of f. So it'll be 1 over x plus 1. And now we talked about how to clean that up. Last unit, or a couple units ago, we reviewed that if we want to simplify this complex fraction, you look for the little denominators. In this case, it's just x. If we want to cancel x, you can multiply both numerator and denominator by x. So when you do that, x times 1 is x. Here you're going to get 1 plus x. Oh, you know what? I just realized I made a mistake. So after I plugged in this into x, I forgot that there was a minus 1 there. So let's make that adjustment. Okay, so these 1s actually end up dropping out. So let me rewrite this. Sorry about that, guys. So then really what we have is 1 over x. Okay, and you could do this the way we've been doing. We still have to get rid of that little x. So multiply top by x, multiply bottom by x. We get x over 1, which is x. Okay, so that part's good. And now if I go the other direction, g of f of x we take all of f and plug that in to g. So now if I look up here, all of f is going to go right in here into this x value. So we're going to have 1 over x minus 1, and then plus 1. Okay. Again, if we clean that up, we can multiply this by x minus 1 to cancel out the little denominator. So then when I do that, in the numerator you get x minus 1. And then in the denominator, this will cancel the x minus 1. That was the point. We just get 1. Okay. Dividing by 1 doesn't do anything for us. It just leaves the numerator alone. So we get x minus 1 plus 1, which is also x. Okay. So these work, again, with the assumption that we have whatever's on the inside here, that's g, right? This only works as long as g is as long as x is not 0. And here we have f on the inside. Our restriction for f was that x could not be 1. Okay? And since we got x both times, okay, we're going to say yes. F and G are inverses since both f of g of x and g of f of x equal x. Okay? All right. So now we're going to go ahead and go on to the second half of the section. Okay? Here we're going to focus on finding inverses. Okay? In the first part of the section, we just kind of learned about inverses, learned that x's and y's reverse, inverses undo the original function, domain and range flip-flop. Now we're going to talk about how to graph inverses and also find the inverse. Okay. First, this is kind of nice because it's a good way to check that we're graphing things correctly. Y equals x is a symmetry line for the original graph and the inverse of that. Okay, so this composition over here, where we get f of g of x and g of f of x to equal x, that's not a coincidence that then we end up with x as our symmetry line. Okay, so that's kind of why you see this y equals x line drawn in there. It's kind of to help you. All right. As far as using the graph to find the inverse, or to draw the inverse, this is so easy, guys, because we don't have to do any algebra. All we're going to do is just reverse the x's and y's. So I'm going to start with this point. -4 comma -4 turns into, well, if I reverse x and y, it's actually going to stay in the same spot. Okay? But now -3 comma 1 becomes 1, -3. Okay? So all we've done is taken the x and y, we've flip-flopped them, and now we have 1 comma -3. 1, 2 becomes 2, 1. So we go 2 to the right and 1 up. And then 2 comma 5 becomes 5, 2. So 5, 1, 2. And those are the points of the inverse. So now to graph your inverse, since these were just basically connecting the dots, we're going to do the same. And right here is that symmetry line, right? This is exactly split right down the middle of the picture. This side and that side are mirrors of each other. That's how we know that we've drawn things correctly, or that our graph is correct. Okay? With B, it's kind of a smooth curve, but now we have -5, -5. Okay? If we flip-flop those points, we're still going to end up being at -5, -5. Now over here, where I have 25 over 12 for y and 5 for x, we reverse that. 25 over 12 is just a little bit larger than 2. And then we go up to 5. Okay, so we have that point. And there's one other point on the graph that we can use. 0, 0, if we flip-flop, will stay at 0, 0. Okay, so we have this point, and that point. And now we're going to use the shape of the graph since we don't really have much else to guide us. If I'm going like this on the left side of y equals x, then I'm going to mirror that and do something similar down here. Okay, and now the graph goes underneath the line y equals x. So from here I'm going to go over the line and do something like this. Okay, and you can kind of see now if you check the mirror line, that looks pretty good as far as being mirrors of each other. Okay, so that's graphing inverses, and like I said, a lot of this stuff's pretty easy. If you have to find points, you just reverse the points. If you have to graph, look at your graph, flip-flop all the coordinates, plot the coordinates, and then connect the dots. That's pretty straightforward. As far as finding an inverse, okay, so that's a little bit trickier, but it's not too bad once you kind of see how it works, okay? So this is a nice summary here. Anytime we see f of x, we want to think of it as a y. And as we've been saying earlier, that for inverses, x's and y's just flip-flop, that's exactly what we're going to do in the equation. We're going to reverse x and y, then we're going to get y by itself, and whatever formula I end up with, that is my inverse, okay? So I'm going to do those steps right here. So here they give us the conditions that x cannot equal 1, which makes sense, because otherwise if it were 1, we wouldn't be able to do this. And it is 1 to 1, so we're going to go ahead and find the inverse. Remember that this is y equals 2x plus 1 over x minus 1. Now we could go ahead now and switch the x's and the y's. So that's my first step. Now I want to just, here I want to get y alone. Now, since I have this denominator down here with y minus 1, I'm going to multiply both sides by y minus 1. So now I get x times y minus x on the left-hand side. And on this side, the y minus 1 cancels out. We get 2y plus 1. And just like any other algebra equation that's linear, not a quadratic or cubic or anything that hard, we're going to try, since we're trying to get y alone, we're going to move everything so that the y's are on one side and everything else is on the other side. So when I do that, xy I'm going to keep right here on the left. This positive 2y I'm going to subtract over. So now I have the y's together on one side. My other terms right here, negative x and 1, I'm going to leave on the right-hand side. So this negative x I'm going to add to the other side, and this plus 1 will stay. Okay, now the point of doing that is that this y can now be factored out because we're trying to get it alone. If we factor out a y, we get x minus 2. Okay, and then from here, since we have y times this entire thing, okay, to get y alone, I'm just going to divide by x minus 2 on both sides. So then now here, the x minus 2's cancel, and now I get y equals x plus 1 over x minus 2. Okay? And so we're almost finished. This is just a placeholder. What we really cared about is this formula over here on this right-hand side. That is the formula now for the inverse of f. Okay? So to recap, you flip-flop your x's and y's, then you try to get y alone. Once you have y alone, that formula, that's going to be the formula for your inverse. Just remember to swap out the new y that you obtained with the inverse. Okay? Let's keep going here. Example 3. So here we're finding the inverse of y equals f of x, which is x squared, but only where x is greater than or equal to 0. Okay? We're also going to graph y equals x, we're going to graph f, and we're going to graph the inverse. Okay? So I'm going to start with y equals x. Y equals x is easy. That's just this straight line. Y-intercept is 0, slope is 1. So here's y equals x. Okay. We want to graph the parabola x squared. You guys should know what that looks like by heart. If not, you could plug in starting with 0. Plug in 0, you get 0. Plug in 1, you get 1. Plug in 2, you get 4. So hopefully you remember that your graph kind of looks something like that. Okay. We don't want the left half of it because it says x has to be 0 or higher. You know what? I might as well. I don't even need to find the inverse rule. If I have points, I can just flip-flop all those, okay? So to graph the inverse, 0, 0, just like we did earlier, will stay 0, 0. 1, 1 will stay 1, 1. But this point that was 2, 4 is going to become 1, 2, 3, 4 for x, and then 2 for y. And so here are your points for the inverse right here. And you can connect those, and it should, again, look like a mirror. So the pink graph that I have goes just a little bit above the green line and then cuts through it again and goes under, and here's my mirror line. Okay? So now let's find everything else. The restricted domain, well, they gave it to me right there. It's x is greater than or equal to 0. If I look at the purple graph is f. The pink graph is the inverse. Okay? The range for the purple graph, that's the y values. The lowest y value is 0, and then we go to infinity. Okay? So now that means, and by the way, this is also 0 to infinity, right? You could either write it that way or in interval notation. The domain and range will flip-flop. So if the domain is 0 to infinity, the range for the inverse will be 0 to infinity. And same with the range, that'll become the domain. These are all 0 to infinity though, so that's not too bad. All right, and now we can find the inverse. So we have y equals x squared. First step is to switch the x's and y's. And now we try to get y by itself. Well, this one's pretty easy compared to the last one. To get y alone, to undo the square, we square root both sides. And so y would be plus or minus the square root of x. Except for the fact, though, that right here we know that the range is 0 to infinity only. We could also see it on the graph. We don't have positive root x. We only have positive root x. We don't have the negative portion. So when I write my answer, I'm just going to say y equals root x only, and that is the rule for my inverse. Okay? All right, I know this is kind of quick, but I'd rather make sure we have everything down and then spend time, practicing and getting help and deciphering all this stuff. Okay, example 4 is the application portion of the unit. If we read it real quick, we have a formula that tells us the distance. This is distance right here. D is distance in feet. Required to stop a vehicle, a car, traveling a speed of r. So r is our speed. Okay. So if I wanted to know how long it would take my car to stop if I was traveling 45 miles per hour, I would just plug in 45 into r and then calculate that distance. Okay. So let's see what they want us to do. Part A says express the speed r, so that means get r alone as a function of d. Okay, well that makes sense. Let me rewrite it as, we want to know what r of d is. In other words, take the formula they give you right here and just solve for r. That's all we're doing. Okay? So I'm going to just kind of do that right here. I'm going to rewrite it just as d so we don't get confused. First, I'm going to add 90.39 to the other side. And now if I'm solving for r, then I just need to divide by 6.97. Okay? So my final answer, r will be d plus 90.39 over 6.97. And this is now a formula in terms of d. So instead of f of x, and then we see x's on this side, here we have r of d, and we see d on the side for the formula. Okay, that's part A. Now they want us to verify that r equals r of d is the inverse of d equals d of r. So anytime we verify things are inverses, we make sure that we get the compositions basically to cancel each other out, and we're just left with our input, which in this case is r, and in this case is d. Okay? Not a huge fan of this problem, guys. I'm going to be honest. I don't like that they're not switching the variables, which is what we're supposed to do with cost anyway, or with x's and y's, but it's the same idea. Okay, So let's find r of d of r. Well, d of r was given to us. It was 6.97r minus 90.39. And now that's going to get plugged into r, which is down here. So this gets plugged into the input here, which is d. So that'll be 6.97r minus 90.39 plus 90.39 divided by 6.97, which, if you can simplify right away, you see the 90.39s cancel out, and then it's just 6.97r over 6.97, and so we certainly just get r, so that's good for the first part. Now for the second part, I'm just going to try to squeeze that in right over here. We want to find r, backwards. We want to find d of r of d. So now I take r, which is d plus 90.39 over 6.97, and that gets plugged into the d equation, which is up here. So I'm going to take the r and replace it with all of this stuff. So now it'll be 6.97, and instead of little r, we're going to replace that with d plus 90.39 all over 6.97. And then don't forget to subtract 90.39. Right away you can see, oh look, 6.97's cancel. We're multiplying and dividing here. So now we just get d plus 90.39 minus 90.39. Those cancel, and we do get just d. Okay, so that's what they wanted us to do there to verify that they're inverses. Final question for the notes. I know that was kind of lengthy, I apologize, but got to get this stuff done, guys. This is a college class after all. Okay. Predict the speed that a car was traveling if the distance required to stop was 300 feet. Well, now we have a formula for speed, which is r. I got that right up here. We're just going to plug in the distance required, which was 300. Okay, so that'll be 300 for d plus 90.39 divided by 6.97. Type that into the calculator, and we get about 56 miles per hour. Okay? All right. That will be the end of that.